If now internet is using megabytes per second, the terahertz frequencies, and specifically the frequencies where fused silk is transparent, is in gigabytes and petabytes.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Materials Science and Engineering explores the basic structure, properties, and behavior of materials, down to the molecular, atomic, and even subatomic levels, to create goods that benefit society. From prehistoric stone tools to modern-day silicon semiconductors, materials have served as critical building blocks for the technologies that people depend on every day. We're joined today by Nicholas Kotov, a professor and director of the NSF Center for Complex Particle Systems, a multi-institutional effort that works to advance the design and manufacturing of complex materials. Professor Kotov, thank you so much for taking the time to speak with me today. The specific piece I want to start with, your group is part of a larger collaboration that's made a fused silk material. So I want to ask you, what is fused silk and how has this collaboration made new materials out of it?
Fused silk is interesting type of a new material that combines order and the disorder. Silk itself has its unique properties due to the fact that parts of silk fiber are crystalline and parts of it are amorphous. And for a long time it was a problem how to make silk-based materials that would be formable and that would be not in fibrous form, but maybe in the blocks. And I joined the collaboration with my colleagues from Imperial College London when they already developed that technology, how to transform fibrous silk into bulk silk. The chemistry of that is quite interesting. They used high pressure and moderate temperature in order to melt just slightly the amorphous part and keep the crystalline part. And when amorphous part fuses together, the fibers produce the monolith, a continuum. And my part of this collaboration was to establish the new properties that are unusual for such type of materials. By using the previous knowledge about this combination of crystallinity and disorder, I found that we can have very strong polarization rotation, new optical properties in terahertz part of the spectrum.
I would like to unpack that a little bit because I think the general public will think of more the fabric, like maybe our tie would be made out of silk or something along those lines. So you mentioned the crystalline aspect, and I'm sure that's how it gets optical properties. But can you pull that apart a little bit for what those optical properties might mean for like the common person?
Silk, which is typically, as you said, a fabric, has actually quite interesting properties in optics. That requires understanding in which part of electromagnetic spectrum we are looking for these new optical properties. And silk fibers are in millimeter range. If we fuse them and produce a continuum of this crystalline disordered domains or this sequence, we will get to sub-millimeter part of the materials organization that will be very good for sub-millimeter wavelengths. And that brought me to the idea of looking into transparency. This is an optical property in the sub-millimeter wavelength of frequencies, which is the terahertz wavelengths. It turns out that components of the silk, this combination of nanometer and micrometer scale substructure of silk, leads to not only some transparency and opaqueness in the terahertz range, but also very unusual property of polarization rotation, because silk is a biological materials, it chiral materials. It's actually very similar to a lot of other chiral materials which have that polarization or rotation activity.
What sort of public uses might these materials end up being useful for?
Right. It's actually very interesting to look at this range of frequencies. Um, and actually, the idea of that came to me when I was passing through the security screening in the airport. You possibly remember that they receive an image of you with all the clothes and everything. And it means the clothes and some other tissues are partially transparent, at least. If it is metal, it's not transparent. So in terahertz, we enter the region where the fabric is still transparent, but acquires this very novel optical activities which are related to its organization. The terahertz range is the future of the telecommunication. We all use smartphones, we all use Wi-Fi. It's typically 5G, maybe 6G in the future. But if we are looking what frequencies it will be terahertz frequencies. And they're advantageous because they allow very high throughput. A lot of data can be pumped and exchanged in between the users and servers. If now internet is using megabytes per second, so the terahertz frequencies, and specifically the frequencies where fused silk is transparent, is in gigabytes and petabytes. Intelligence and all the exchanges, we have to have these new frequency ranges. So we need to develop this optical the devices and optical materials. They are needed not only to ensure the fast exchange rate, but also to avoid hijacking. Or if somebody can hijack your burst of data, that would not be good. And you don't want that, especially if you have a lot of data. And what we observed in these materials was ability to rotate the polarization of light, and that enables you to dial in the capabilities of how secure your communication is. This ability to polarize light and to rotate it enables you to include filters on the receiving end, filters on the emitting end, and to code your data to the very high degree of security.
That's very cool. So to kind of simplify it, this could be very useful to replace fiber optics or interconnects in different optical systems with, like, as we get to the supercomputers and maybe quantum computers and these kind of things. And then you can polarize it to kind of build in its own security.
Absolutely true. We need to think about how do we ensure the world where the communication is secure. Maybe this type of technology will replace parts of fiber optics. Maybe it will be a different type of a communication platform. But the ability to transmit the data fast and transmit it at the multiple levels of security and of including the code for it, I think will be very critical for the future of data in our world and the future of humanity too, that reason.
So thinking about getting it to market, I guess, what kind of needs to happen next for this to go from like the benchtop lab to real world use?
I have been thinking about that too, Nate. And this is a very exciting area. So I'm thinking about starting a company for manufacturing of these new materials in the United States. It might not be from silk, it might be based on the knowledge that we established from this study. Because silk, as wonderful as it is, can be used for some lenses, for instance, for some polarizers. But we also need to add more properties to have very kind of adaptable material that would have both optics and strength, and, for instance, resistance to um, environmental conditions. This type of materials that will be able to combine both electronics requirements and this new terahertz optics requirements is the next step. And I already have a pretty good idea how to engineer them. And I'm thinking what will be the pathway for their scale up.
So, taking the learnings from all the various other materials you've worked on over the years and kind of working into what might be the better path forward. So, speaking of all of these other things you've worked on, I'd love to dig into some of your other work. And your lab, and you're the director yourself, is part of the NSF Center for Complex Particle Systems. Can you talk a little bit about this center and what sort of work is being done there?
Oh, Nate, absolutely. So it's very cool that you asked about it because this work with Imperial College London and Tufts University and the university in Austria, this is a part of our effort to understand better how to engineer these materials, combining order and disorder, just like so. And it turns out that at the moment we don't have good tools in order to engineer these complex materials. And complexity here is indeed a combination of order and disorder that complements each other, that enables us to create these materials which have property sets that in the past were thought to be really impossible. For instance, how to be conductive and transparent, how to be light and super strong, how to have polarization, rotation in terahertz, and environmental stability. These are the tools that Compass, the Center for Complex Particle System, is developing. Its goal is to create the fundamental workflow for engineering of these materials where disorder is a part of the design. And we used to have engineering a lot of materials which have crystallinity, like semiconductors or maybe some even crystallization of drugs, but we don't have good toolbox when we combine both disordered part, amorphous part, and very ordered part, which complement each other. And Compass is developing this toolbox based on the graph theory, which enables you to have a quantification of both organization and disorganization. It has the parameters which describe long-range order and short-range order. It has the parameters that describe some stochasticity of the material. The challenge here is how to translate that fundamental knowledge into practical manufacturing of the material. The goal of Compass is not only to have the cool mathematics, but also has the mass to manufacturing workflow. How do we start with design of the materials, with what we need, for instance, for the terahertz optics for a specific case, or for membranes in other case, or for catalyst in the different case, or for ultrasonics in some other super strong materials. All of them have to have this combination of unusual properties. And in most cases, it comes through this integration of order and disorder. So we not only creating the mathematics component of that, establishing the nanoscale methods of their self-organization, but also creating a loop how eventually to accelerate that process, translating it to the manufacturing, not in 10 years, not in 15 years, but much more rapidly in 6 months.
Right. You have to figure out the good workflow for how to do it, and then teach the people what it is and how to adapt to what they've been doing to use the tools. Yeah, that's cool work.
You're totally, absolutely on target there, Nick. I couldn't say it better.
I also want to ask you about your NSF support over time. Like, you got a career award back in the 1990s. How has NSF support impacted your work?
Nate, I remember that conversation so vividly. It was a couple days before Christmas. I received a call from NSF, and the program manager says, Nick, you got a career award. I don't remember a better Christmas present in scientific terms. Yeah. It was absolutely critical for the start of my career, and career of many other people in my shoes as well. And I started in Oklahoma, so it's not in Michigan. So I started in Oklahoma State University in Stillwater. So it is a great school in many ways, and I'm very grateful for my time there. And it enabled me to start the lab right. So that award was very critical for asking the questions beyond the horizon. So what is possible and what the humanity and United States will benefit from, not just as an immediate, say, paper, but also in 5 years, in 10 years. How can I think about challenging problems that will determine the technology which is actually operational right now. So if we, for instance, look at graphene and graphite-based technology, that is based on self-assembly that I started working on at that time. So it was indeed a very essential kind of leap forward that enabled not only something maybe low risk, low reward, but high risk and high reward, how the United States should operate.
You said beyond the horizon in your answer
Yeah.
there. And I want to think about the future for my last question here. What are you most excited to work on over the next couple of years?
I'm, as you might feel, I'm very much excited about what I'm doing right now. So, Compass is a very important part of my life, actually. And I am very much committed to this NSF Center, making sure that what we envision, that a translation of deep scientific understanding of order and disorder, how to describe it by using graph theory, and how to translate it without any interruptions into something tangible. This is what I'm very much excited about. I also see the new AI capabilities that we can integrate with. So, graph theory in terms of materials plus AI, this is a very potent scientific combination. It's a cauldron of new technologies, and one of my focus areas in that engineering aspect, how to combine AI and graph theory in seamless manner, would be directed toward two things: new membranes for batteries and terahertz optics for 6G and 7G.
Special thanks to Nicholas Kotov. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.